Hello everyone. Today in our mathematics experiential learning project, we are going to explain you about Laplace equations and its applications. So first of all, we'll see the introduction of what Laplace equation is. Basically, the Laplace equation is a second order partial differential equation and it is denoted by the symbol of by this symbol. It is a useful approach to determine for the determination of the electric potential in free regions of space. The Laplace equation is derived to make the calculations in physics easier and is named after the physicist Pierre Simon Laplace. We'll see now why do we need Laplace equations. So basically, anything which is directly related to a linear differential equation can be usually solved using the Laplace equation. Differential equations occurred mainly in physics, mathematics, and engineering. The Laplace equations are used to describe the steady state conduction heat transfer without any heat sources or sinks. There are various other areas where Laplace equations are used, which we'll see further. Now, there are several forms in which we can write Laplace equations. Here are some of the forms in which we can see it. So, in rectangular coordinate system, this is the equation of Laplace equation. Similarly, in cylindrical, spherical, and curvilinear coordinates also, we can express Laplace equations. Now, we'll see applications of Laplace equations in mechanical engineering. So basically, the Laplace equations is a fundamental equation in mathematics, as we have seen earlier, and it has various application in the field of mechanical engineering. First application is it can be used to model the stresses and strains in a material. However, we'll illustrate how Laplace equation can be used to model stresses and strain distribution. First, we'll take an example of a cantilever beam, which is subjected to a distributed load. Let the beam has a length B and width B, and it is fixed at one end and free at other. Now the distributed load is at a constant pressure of Q that acts over a beam. Now, to solve the stress and strain distribution in the beam, we can use the Laplace field U of x comma y comma z and form the equation. Now, so through various equations, we can relate the displacement field to the stress strain field using the following equations. And by applying the boundary conditions and solving the Laplace equation, we can obtain the displacement field. The above equations can be used to compute the stresses and strain distribution in the beam. The resulting stresses and strain distribution depend on the material property of the beam, the dimensions, and the magnitude and distribution of applied load. So in summary, we can say that Laplace equation can be used to model distribution of stresses and strain in the material, and this information can be used to design and analyze. Now we'll see other applications of Laplace equation.
So the first application is circuit analysis. So basically in circuit analysis, in majority we will discuss the how the S domain is converted into time domain. So when we put in circuit input that or circuit variable, there is a response which plot the function and time graph. So all the inputs including unit step, ramp, impulse, exponential, sinusoidal, and others have been introduced as a time dependent variable. So this demand of use of time domain differential equations and solutions. There's a high order circuits or on the other hand produce high order differential equation. So we might be able to solve these depending equations in the beginning conditions. So here we explain a particular equation with the help of example. So the Laplace equation transform is often used in circuit modeling to analyze the behavior of circuits in frequency domain. So there is the equation that is Fs equals to integration from 0 to infinity e to the power minus st f of t dt. Here we converted the frequency domain into S domain. So there's a several steps that is in first step there's a transformation of time domain circuits into S domain circuit. Afterwards we solve the S domain circuit like example nodal analysis or mesh analysis. Further in step 3 transformation of solution back into time. So there's another example that is the V naught T, which is given in the form of V naught at 0 is equals to 5 volt. There's a circuit which consists of the resistor and capacitor. So here the frequency domain is basically converted into S domain. So there's a further calculation is here.
Now I'm going to explain you about control engineering. In mechanical engineering field, Laplace transform is widely used to solve differential equations occurring in mathematical modeling of mechanical system to find transfer function of the particular system. Following example describes how to use Laplace transform to find transfer function. For example, if we take a tank shown in figure that is initially empty at t is equal to 0, a constant rate of flow Qi is added for t greater than 0. The rate at which flow leaves the tank is Q naught is equal to Ch. The cross-sectional area of the tank is A. Determine the differential equation for the head H, identify the time constant and find the transfer function of the system. So we solve it using the equation given Q naught is equal to Ch, where m is the mass of the fluid, E is the density of the fluid, mass is equal to volume into density, that is A into H into E. Now we find the mass flow rate, which is dm by dt. After differentiation mass with time, we get a mass flow rate. So mass flow rate into the tank is equal to mass flow rate minus mass flow in rate minus mass flow out rate. Now we can solve the above derived partial differential equation using Laplace transform on both the sides, and we can get our desired result.
Now I'm going to explain the application of Laplace equation in automatic control, a mechanism where it is involved electrical, mechanical, or other principle designed to accomplish such automatic control is called servo mechanism. Suppose that a missile M is striking down enemy aircraft. If at time the enemy turns through some angles and the M must also turn through this angle, it is to be catch the destroy and to destroy it. If a mass was absorbed aboard M, he could operate. In this application, let us assume that the desired angle of turn as indicated by the radar beam is theta. Also, let denote the angle if turned by the shaft at time t. Because the things are happening so fast, we must expect to have an error between two. Let's suppose error is a function of t, which can be explained as theta t minus alpha t. Theta t is equals to minus alpha t. That is, the existence of error must be single back to the shaft so that compensating turning effect or torque can be produced. Torque can be presented as I d square by dt square. That is moment of multiplied by angular in acceleration. Since torque is directly proportional to angle theta, and k is greater than 0, the minus signal is the minus sign used to be determine the direction of the turn. And the other application of Laplace equation is digital signal processing. Revolving a discrete digital signal is a bit difficult due to the step-by-step analysis of the and continuous analysis. This is because the digital signal can be broken down into the small parts, and the small part can be called the impulse, which can be the proper time-dependent function. The signal is converted to frequency domain to a specific case of Laplace that can be used with Fourier transformation, and the other name of Fourier transform can be used as jet transform, which is the very specific case of Laplace transform to convert the digital signal processing into analog signal. Here we conclude our Laplace, our mass here, that is the Laplace equation and its application in the mechanical and the engineering world. Thank you.
Thank you.